decreasing. So we will look at the graphs so that you can see what the shape of these graphs look like. So we'll look graphically what they look like. And then there's a lot of applications with exponential functions. So things in life grow exponentially. Populations grow exponentially. So that means it's going to be increasing at a certain rate. You would hope that money grows exponentially. Right now, the stock market is kind of a little watery if you've been watching any of the news. But you hope that you grow with money. Interest is another thing, that if you buy a house, you buy a car, you have a credit card, interest, you're gaining interest, and that's the money that you don't want to grow, but the longer you have it, the more money you're going to have to pay eventually. So all of those things kind of are correlated with this exponential growth. So an exponential function, nobody has their own credit card, right?
I have a debit card.
Okay, debit card is okay, good, that's fine. A debit card is good, because you have a limit as to how much you can spend there.
You can spend over the limit.
Oh, well, then it gets deducted, and you get a fine.
7 was over.
There's a little fine.
Oh, little Sam apparently knows, because he's done it for so long.
No, I haven't. I just done a little thing.
Alright, that was weird.
Alright, so our exponential function looks like y equals a b to the x. So the part that's to the x is the b. The a is separate, so it's not like that x gets distributed to both a and b. So the a is totally separate, the b is the part that gets the exponent. That's the part that's going to change. So anything that has an x with it is the part that changes. So a would stay constant, but b is going to be changing. Couple of things here. A can't equal 0, because if it was 0, we wouldn't have an exponential equation. And b is called the base. So it used to be that our base was x and the exponent was 2. So now it's flipped. The base is going to be the number and the exponent will be the power. So in order for a function to grow, we have to have two things that happen. Our a has to be greater than 0. So it can't be negative, because then it wouldn't grow. So it would decrease instead. So it has to be a positive number. And our b value has to be bigger than 1. So those two things need to happen for it to grow. So a has to be positive, and then the b, it needs to be bigger than 1 so that the graph grows. Sure?
That was my question.
Okay. The growth factor is actually the b value. The amount that it'll grow by, that's the growth factor. So are we growing by 2, are we growing by 3, are we growing by 3/2, whatever it happens to be. The growth factor would be the b. So we're going to look at the graph first, and then after we see a couple of graphs, we will start to interpret some equations, some word problems, and how they correlate with an equation. But looking at the middle part of your page, a parent function we've done for every graph so far, starting with the line, which was a review from way back in chapter 1, when we did lines and we talked about slope-intercept form. So parent function is the most basic function, and in this case, it's y equals b to the x. A is 1. That means it doesn't have a steepness to worry about. There's not an initial value sitting in front. Again, b has to be greater than 1. So the parent function with the exponential growth functions with a base of b. So b is my base, whatever number that would happen to be. So it says that the graph rises from left to right. So starting on the left side, looking to the right. That's how you read a book. That's how you read a graph. It's going up. That's why it's growing. So the graph starts and it grows. It grows pretty quickly after it hits a certain point. So there's a point here, and then the next point, it gets higher and higher and higher. That's why it's considered an exponential function, because 1 point over, 1 x value over, it's going to get even higher, because it's an exponent. So you're squaring something, you're cubing something, you're taking something to the 4th, and those numbers get pretty big. The left side of the graph, this part here, it kind of just tapers off and it goes horizontal. So eventually the numbers are going to get so teeny tiny that it's just going to kind of level off and almost appear to be horizontal. So at the bottom, can anybody kind of describe what the domain would be in interval notation? So thinking left to right. Virginia?
Would it just be
Yeah, it's negative infinity to positive infinity. That's the domain. Because you can plug in any number for x. My exponent is allowed to be any number. So I could plug a negative 2 in, we could plug 100 in, we could plug a negative 1,000 in. X is allowed to be anything. What do you think the range?
What if you plug in 0?
Anything to the 0 power is 1. Yeah, so you can plug in a 0.
Well, no, what's something to the 1?
But whatever this number is, then it would be itself. So if it's a 2, it would be a 2. If it's a 3, it would be a 3.
Wait, but if anything is to the 0 power, then like if 24 is the 0th power, that
It's-
means 1.
It's still 1. Is it?
What if it was like x was like a negative number? Where would the graph go?
I'll show you. We're gonna do like I promise. We'll do a graph that has a negative number. I promise. We'll do a lot. Sarah,
I was just.
give you the range. Oh, perfect. What's the range?
Wouldn't it be 0?
Yeah, the range is from 0 to infinity. So it's never going to go below the x-axis. It'll always just kind of like skim next to it. But it will never actually touch the x-axis either because it can never have a y value of 0 because of the exponential part. So there's no way that I can get any number that'll ever be 0 because I'm always taking like a number to a power. And any number to a power will never make 0. The only way we can make 0 is by multiplying by 0. Dividing. Can't divide by 0. So it's 0 with a parenthesis and infinity with a parenthesis. Is it?
Wait, so would the graph going to left would just like keep getting like infinitely smaller, but like not actually?
Right. So like you can't physically see that it's getting smaller, but it's just going to get like.
But it doesn't level out.
It kind of levels out, but not like technically. No, it never gets horizontal. Alright, so I want to show like if you look at the next problems, I think you'll see like how those numbers are working, why they're never touching 0. It'll make a little more sense when we look at some numbers. So we're going to graph these. The great thing about chapter 7 is that I finally got around to making a test that has a calculator portion and a non-calculator portion. Exciting, right? Which I should have done for chapters 4, 5, and 6. We should have had like a calculator portion and a non-calculator portion. The graphs will be on the non-calculator portion. So it makes sense. Like, you need to use your brain. Yeah, I know you got that calculator, like, but how does that brain work a little bit to help you out? So when you go to do your homework, and today in class, I strongly suggest that when you're asked to graph, you don't rely on the calculator. Because it's not going to be there to help you on the test. So use the mental capacities that you have in your brain. We're going to make a T-chart, just like we have for every other graph that we've done. Picking 5 numbers. These 5 numbers you don't have to think about. Whereas like the radical problems, we had to think what 5 numbers are good. It's just -1 or -2, -1, 0, 1, 2. So you don't have to think about those 5 numbers. Just use the 5 basic numbers that we have. Okay, so again, try not to rely on the calculator. I know it's hard, but you're going to do this mentally because you're going to have to do it on the test. Virginia.
But you said we were doing negative numbers for x.
I said you could have negative numbers for x. The y can't be negative, but you're allowed to plug in. We said negative infinity to positive infinity for the domain, so that means anything can be plugged in for x. It's just when I get a number out of it, it's not going to be negative and it's not going to be 0. Okay, so when you plug a number in, once you see how a couple will work, I promise it'll be a little more straightforward. So we have 1/4 times 6 and then to the -2. So you need to think from the 2 chapters that we spent with exponents, what does a negative number as an exponent do? It moves it to the bottom. So this is really saying we have 1/4 times 1/6 squared. So the only part that moves is the part that's connected with the negative exponent. So that 6 goes to the bottom of the fraction. One more time here, this is 1/4 times 1/36. So 6 squared is 36. So now, in your head, I know this is a little tricky, but we're doing 36 times 4. So, who said it? Somebody said it. 144. There's a 1 on the top, and then 144 on the bottom. So 1/144, is that a big number or a small number? Really tiny. So if you make this a -3 or a -4 or a -5 or a -6, the number on the bottom is going to get bigger, but that makes the whole fraction even smaller. So is it like that kind of like that number? This is just going to get tinier and tinier and tinier, but physically we can't graph it or see that it's getting smaller and smaller and smaller. So when you have a number on the bottom of a fraction, it means that that's just an extremely tiny little number. So if you look at the second one, we have 1/4 and then 6 to the -1. You'll get the hang of it with those negative exponents. So that really means it's 1/4 times 1/6. Negative exponent makes it into a fraction. And that number is 1/24. 4 times 6, both on the bottom of the fraction. And then the third one, 6 to the 0, we just said was 1. So 1/4 times 1 is 1/4. So then I would have 1/4 times 6 to the first. So what's 1/4 times 6? 8. 3/2. And then finally, 1/4 times 6 squared is really 1/4 times 36, and that makes a nice number of 9. When you're multiplying by 1/4, you're really dividing by 4. All right, so when you graph this extremely tiny little number, 1/144, physically, I mean, we're going to make it as best as we can, but it's extremely tiny. So go over to -2, just go slightly above the x-axis. That's where 1/144 is going to be. That's how we can graph it. The next one at -1, we're just going to make it a slight increase. It's not much because it's 1/120, or it's 1/24. And then at 0, we're at 1/4. So you're like just a little bit above. Those points really are like really close vertically with each other. And then it starts getting easier. So at 1, we're at 3/2 in the middle between 1 and 2. At 2, we're up at 9. Just make a point above on the graph. So when you connect this, like my points would just continue to get closer and closer to 0, but they're never going to touch because there's no exponent that would make a number 0. So it kind of gets horizontal. Visually with our eye, it will look like it's getting horizontal, but it really is just continuing to like very teeny tiny decrease. So underneath this, it asks you to get the domain and the range. So looking at your graph, Sam, domain is left to right. So what does it look like the domain is?
-infinity to positive.
Yep, -infinity to positive infinity. And then what about the range? 0 to infinity. And again, it will never touch 0. It can't be 0. And it will.
Will that always be the domain and range?
For the problems that have no translation, yes. So when we switch the page, you'll see why the range may change. The domain will not. Because you can always put any number in for x. So the domain will not change, but you'll see how the range changes a little bit. So I'm going to erase my work over here. I would like to see if you can try the second graph. Make yourself a new t-chart. This one's easier because you're multiplying by a 1/2 instead of a 4. So it makes the numbers a little easier. So plugging in -2, -1, 0, 1, and 2. So we would have 4 to the -2. Which really means you're taking 1/4 squared. So what's 1/2 times 1/16? Virginia?
1/32.
Right, 1/32. The next one, we're taking 1/2, 4 to the -1. So that's really 1/2 times 1/4. Virginia, 1/2 times a 4 makes 1/8. So plug in a 0, plug in a 1, plug in a 2. Once you get to 0, it becomes a little easier. You're not worried about the fractions. So the negative exponents are going to make a fraction. That's what a negative exponent does. Does anybody have the 0, 1, 2? Mason, what do you got? 1/2. And 1 is?
0.
And 2 makes? So 4 to the first is 1, 1/2 of that is 2. 4 squared is 16, 1/2 of that is 8. So over to -2, again, 1/32 is still really tiny. And then 1/8 is just slightly above it. And then once you get to 1/2, you can see that it does start to grow. So my 8 will be above the graph. So these graphs, like visually, they don't look any different from each other because the numbers are so tiny, like with the negative exponents, that they look pretty much the same. But looking at the numbers, you can see the numbers are different in the t-chart, but I mean, they look very, very similar. So domain, negative infinity to infinity, and then the range, again, 0 to infinity. All right, questions? So Kate said, when does the domain or range change? And I said the domain never changes, but the range is going to change when we apply a translation to the graph. Translate's another way of saying move, slide, shift, whatever word you want to use. So to graph a function in the form a, b to the x minus h plus k, so h and k are back in the problems. Begin by sketching the original graph, a, b to the x, which is what we just sketched over here. So that's like the original graph, a, b to the power of x. So we're going to sketch that. And then it says translate the graph horizontally with h. Remember, h goes left and right, and it's always the opposite of what you see. Vertically with k. So h and k are still part of the equations, and I'll show you how we're going to use them in a little bit. So we're graphing y equals 2 times 3, and then it has x minus 2 as the exponent, and then a big minus 2 next to that, as like a whole number being separate. What we are going to graph would be the easy part, the 2 times 3 to the x. We're going to ignore the 2 minus 2's for now, and I'm going to show you how we'll use them to make a graph. So we're taking the 2, the base of 3, and just the exponent of x. It makes it a lot easier to do the numbers if you don't have those extra values being added into the problem. When you graph it, make it a dashed line. So we're going to graph this. We're going to make it a dashed line to show that it really isn't our final graph, or we're going to use it to create a final graph. So when you plug in those numbers, you have 3 to the negative 2, which is really taking 2 times 1/9. So the negative exponent bumps it to the bottom. 3 squared is 9, so now it's 1 over 9, or 2/9. So 3 to the negative 1 is 1/3. So 2 times 1/3 is 2/3. So if x is 0, what's our y value? Okay, 2, because 3 to 0 is 1 times 2. Okay, if x is 1, our y value is 6. And then if x is 2, the y value is 18. That's good. So 3 squared is 9. 9 times 2 makes 18. So we probably won't graph that because it's pretty far off our graph, but we have it there to look at. So with a dashed line, after you plot your points, make it a dashed line. And that shows us that it isn't exactly the final answer, but we're going to use it to help us get that final answer. So again, you don't have to graph 218. You don't have to graph that last point. So you're going to make it kind of look horizontal on the left side, and then it attaches to those points and it grows. And I didn't make mine dashed. Make yours dashed. Alright, so then it says, after you graph the basic graph, we're going to try and translate it. Move, shift, slide. Looking at the equation, if it says x minus 2, how is that affecting the graph? Eric.
Move it to the right.
Right. So this moves it right to, even though it says minus, it's moving it the opposite direction. And then Aaron, the other minus 2 moves the graph down 2. So we're going to start at each point, and we're going to move it right 2 and down 2. So go to the first point, which is here at negative 2 and 2/9. So I'm moving it right 2 and down 2. My next point was at negative 1 2/3, right 2, down 2. So you're taking your 4 points that are graphed, you're moving them to the right 2, and then you're moving it down 2. That's the easiest way to try and graph when you have those extra values being added into it and you're looking at an exponent. So you need to make sure that your graph looks similar. It should have the same curve, it should have the same shape. After that last point, actually I should say the first point, that's where it kind of just levels off horizontally. Every domain is negative infinity to positive infinity. What is this range? Aaron? Right, -2 to positive infinity. So the part that's making the range change would be that extra number, the k value, shifting the graph up or down. So see if you can graph the second one underneath it, getting those same parts of the graph. It's always going to be a parenthesis because that's the initial 0 value, so it can never be 0. So now if that point is shifted, it's never going to be able to be -2. So it's always going to get a parenthesis. It's never going to be that number. We won't be able to reach that number. Other questions? So for the next one, the part that we're graphing would be the 2 times 4 to the x. Don't worry about the +1 and the minus 3 yet. So graph the 2 times 4 to the x. The negative exponents make fractions. The 6 graphs that you'll have for homework tonight, 2 of the graphs will be like the front 2 that we did. I'm sorry, 3 of the graphs will be like the first 2 that we did, and then 3 of the graphs will have this translation. So for 3 of your graphs, you'll actually be graphing like 2 parts. What did you get when you plugged in a 0?
2.
Plug in a 1.
8.
And then a 2.
32.
Nice. David, how's this graph going to shift? Good. So the graph goes left 1, down 3. So the x plus 1, really it's moving to the left. So taking all of those points, shifting it left 1, and then down 3. So that first point should pretty much be on that corner of our graph. So the domain will be negative infinity to positive infinity. The range is going to be that new shift. So it shifted down to -3. That's going to be the range, the k value. But it will never touch that k value because it didn't touch 0. So that 0 is now just shifted down. So now it's not going to touch the -3. Are there questions with graphing? So the other thing that we're going to look at then are some word problems, and you will need your calculator for these because you're going to be having exponential values and decimal values, and kind of hard to do all of that stuff without the aid of a calculator. So if you want to pull out your calculator if you haven't done so already. So exponential growth models, easy way to kind of model things out in the real world or real life quantity that increases by a fixed % each year. So if something grows by 2%, if it grows by 5%, Or if it's not necessarily a year, maybe it's over a period of months instead of years. And then it says the amount y would be the quantity that you have after t years, so after time. So the equation for an exponential growth model still has an a. And then in parentheses, there's 1 plus r. And then the exponent is going to be a t, since we're talking about time. A is the initial amount. That's what you start with. So if we're starting with the population and like we're starting to do our data like this year, my initial amount of the population would be based off of whatever your year you're starting at. So A is what you start with, your initial amount. R is the rate as a decimal. It's going to be given to you as a percentage. A percentage needs to be converted to a decimal to be applied to the problem. T is time. Inside the parentheses, it says 1 plus R. Why is the 1 there? Not just because it has to be there. No?
It doesn't have 0.
So it doesn't have a 0 in years. Why else would the 1 be there? Thinking about something growing.
When you square a decimal, it gets smaller.
So when you square a decimal, it gets smaller. If that 1 represented a percent, what would the percent be for 1? Aaron? 100%. So if I'm starting with my initial amount, I have 100% of whatever we're talking about. If it's growing on top of that 100%, it's going to be growing by something. So that's why the 1 is there, because you have to start with 100% of your information, and then you're going to increase from there. This is called the growth factor. Now you might see that term used. So 1 plus whatever quantity you're increasing by is the growth factor. If it's bigger than 1, it's growing. If it's less than 1, that's when we would be decreasing or going down. So at the top of the next page, it talks about a buffalo, a herd of buffalo. Over the last 12 years, an initial population of 38 buffalo were in a state park. They grew by 7% a year. It says write an exponential growth model giving the number n of buffalo after t years. So that first part is like we want to write an equation to go along with this information. So that equation needs to look like a 1 plus r to the t. We just need to fill in the numbers. So what's the initial amount? What are we starting with? Virginia? 38. So it says 38 buffalo is my initial population. So that's A. And I guess it wanted us to use an N instead of a Y. Seems weird to have an N over there. All right, 38. What's the rate? How much of the buffalo growing by, increasing by the herd?
0.7. I mean 7%. So
7%.
0.07.
So 0.07. So 7% is really 0.07. And then we're just going to use a t right now for time. So my equation would say 38 1.07 to the t. And then it says how many buffalo were in the park after 7 years. Well, now it's 7 years later. We want to know how many buffalo are in the park now. So the 7 would be the time, the exponent. When you plug this in your calculator, plug it in how you have it written down. So 38 parentheses 1.07, and then your exponent, remember you can use the caret button for the exponent. This is buffalo. Put a little squiggly here, we'll approximate it. We don't want to have like 1/3 of a buffalo. So approximately how many buffalo? 81?
61.
Yeah, approximately 61 buffalo. So now, still with this handy-dandy calculator, we're going to take the equation with the exponent of t, see if we can graph it. So if you go to your calculator and the y equals, we've got 38, 1.07 to the exponent of, we'll use an x instead of a t. Did anybody get a graph?
I got
hit-
part of it.
You can zoom and then
So you can see
zoom
it?
fit. It's
What number is that? 8. Is that 8?
mine is zero.
There it goes. That's not right.
Change the windows.
There we go. Okay, there it is. So in the calculator, if you go to second table, second graph, you don't actually need to graph it, but just using the calculator, it says use the graph to estimate the year where it would be about 53 buffalo. So if you look at your table, what year would be about 53 buffalo? Virginia? 5, yeah, about 5 years. So at 5 years, we have a little more than 53 buffalo. So that's where the table is really helpful. So using the table, you can see that at the year 5, there are about 53 buffalo. So that would be year 5, the 5th year, however you want to state that. Questions? So the last thing that we're going to talk about would be dealing with interest. So this would be an exponential growth model talking about like any kind of population. But there's also something that we have interest. So you earn interest if you invest money. Generally, if you invest like in the stock market or like a long-term thing, that's when you're going to add more money. Putting it in a savings account, you don't really earn money in a savings account at this point. But maybe like grandma or grandpa gave you some money for college, and mom or dad has it invested somewhere that you're earning interest. So when you have compounded interest, that means you're earning interest after a certain amount of maybe time, years. But if it's compounded, it could be compounded monthly, maybe yearly or daily. But the P is your initial amount. It says principal. Principal is the same thing as amount. We still have that 1 plus. It's always 1 plus because you're earning extra money. And then it would be your rate divided by N. And that's the number of times it's compounded. And then that would be N times T. So P is the initial amount of money. R is our rate as a decimal. N would be the number of times it's compounded, and it'll tell you. And then the time in this case is going to be in years. You'll be given all of the information. A is the amount after that amount of time. So your final amount, the end amount that you have, that's what A represents. It says you deposit $2,900 in an account that pays 3.5% interest. So find the balance, which is A, after 1 year if it's compounded monthly. So we just need to plug in the numbers. So the amount that we started with is $2,900. What's the rate if it's 30.5%? Sarah?
0.03.
Right, 0.035. And then N would be the number of times it's compounded. So monthly, how many months are there in a year? 12, that's what that N is. And then that would be times 12, or I'm sorry, to the power of 12 times 1. So when you put this in your calculator, add this together first. But try and keep it exact. So use the second answer function of your calculator. Don't round it. If you round it, then your number isn't as exact. So put this in your calculator, get a decimal value. It's 1 point something. Your answer should be 3003.14. I think the bell's going to ring momentarily, but I want you to be able to make sure you're getting that number. So put the parentheses in your calculator first, get a decimal, but keep that whole decimal. You're taking that to the 12th power and then multiplying it by 2,900. Anybody interested in presenting 35 or 37? How about Sarah and Ka? So Sarah 35,
Yes, sir,
Ka
yeah.
37?
So you guys say after?
Have an awesome weekend.